Thank you for gathering today. For Colloquium this morning, it is my pleasure to introduce Professor Eugene Chiang. In fact, Eugene is no stranger to the Institute, where he was a member here roughly 20 years ago. Since then, he's developed a renowned research career spanning a variety of topics, including planetary system dynamics, protoplanetary disks and their connections with planet formation, debris disks, and star-planet interactions. His contributions have garnered recognition through a variety of awards, including Fellowship of the American Academy of Arts and Sciences, and recently a Simons Investigatorship, not to mention his capacity for mentorship, which has been recognized through the Berkeley Distinguished Teaching Award. Today, he will be teaching us that in the context of planetary systems, some disassembly is required. So please join me in welcoming Eugene to the stage.
Thanks very much, Callum. I really appreciate the very kind introduction and also for the invitation to visit. It's good for me to get out. This talk today it's less about planet formation than it is about planet destruction. It's a fine line, but I think there are many aspects of planetary systems that can be a little hard to understand unless one invokes or counts for some kind of catastrophe. It can be dynamical, it can be collisional, atmospheric, and we'll look at several examples today on varying scales. Just to set the stage for the rest of the talk, here's a plot of everything under the extrasolar sun. So plotting mass. Whoops. Ooh, this was the wrong pointer. Let me go back. The plot shows mass versus orbital distance from the host star. We have the giants on top, and in the lower half of the diagram, there are the lower mass, rockier bodies. If there's one thing that we learned from the Kepler space mission, it is that sub-Neptunes and super-Earths are everywhere. They orbit an order unity fraction of the stars in the universe today. They have masses between 1 and 20 Earth masses, located out to distances of about an AU, almost certainly beyond as well, which will be good news for the Roman microlensing mission. They're everywhere. Even our own solar system has its own set of super-Earths. It's just that they're not so super. We call them Venus and Earth, which I prefer to think of as the low mass extension of this higher mass population. They're all just rocks. And they all form basically the same way from the bottom up, so-called core accretion, small rocks banging together to form larger ones. It takes about up to 100 million years to accumulate the Earth at 1 AU. This back of the envelope calculation is borne out by n-body orbital integrations. It's also borne out by radioisotope dating, which dates the last giant impact that formed the moon to have occurred 50 million years after the birth of the solar nebula. We think that sub-Neptunes and super-Earths formed a little faster. Many reasons for that. They're a little bit more massive. The disks were more massive. They're closer in, so the clock runs faster. But maybe the biggest reason is that they have some gas, right? Some hydrogen in them, which they must have picked up from the primordial protoplanetary disk, which we know lasts from observations. We know they only last for about 1 to 10 million years. How much gas do these sub-Neptunes have? Well, here's where they sit in radius mass space. So the super-Earths, they're basically bare rock, silicate, Earth-like composition, 2/3 silicate, 1/3 metal. But the sub-Neptunes, they're puffier. So they have, according to this color bar here, envelopes which weigh maybe a few percent of the mass, total mass of the object. So modest by mass, but huge by volume. A percent by weight atmosphere can quadruple the size, the photospheric sizes of these planets. I think, and others think, but not everyone thinks, that these envelopes are made predominantly of hydrogen and helium. Basically, because then it's easy to understand this bimodal radius distribution between sub-Neptunes and super-Earths. The super-Earths being the stripped bare, photoevaporated, cores of sub-Neptunes that were too close to their host stars or were too strongly irradiated by X-ray and UV radiation and were just stripped bare, okay? Hydrogen is relatively easy to photoevaporate. Water worlds, not so much. Oxygen, carbon, hard to escape. So we think these are primary atmospheres, unlike the Earth's atmosphere, which is secondary, right? The Earth's atmosphere having a gas mass fraction much lower, 10 to the minus 6, secondary in that it's outgassed from hot rock. These primary atmospheres, we think, accreted from the original disk, but towards the end of the disk's lifetime. So maybe timescales of about 10 million years. And we think this, right, it's sort of the last gasp of the disk. We think this based on calculations like these. This is some calculations of the gas mass fraction versus time that Eve Lee computed as part of her thesis. So if she puts a core into a disk and just watches as the gas accretes on top of it. If she puts these cores, these super Earth cores, in a young gas-rich disk, having a full solar composition's worth of gas, it accretes too much. So it undergoes, the envelope becomes self-gravitating. You basically explode to become a Jupiter, which is not what you want. So you need to stage the appearance of the core later in the disk's life, when the disk has thinned out a bit, by at least 2 orders of magnitude relative to solar composition. But you see here, the good news is that there's a whole variety of depleted scenarios. You can deplete the disk by 2, 4, even 6 orders of magnitude relative to solar composition and still arrive at these percent by weight atmospheres. And I think there's a question from Michael.
I mean, we do know that Jupiter was even hot Jupiter. So could that be a way to make the hot Jupiter?
This is the way. This is the standard way that you make Jupiters. Yeah. Yeah. Of course. It's just that Jupiters we know observationally are rare, right? And so what I'm talking about here is the more commonplace population, which are these sub-Neptunes. Okay. Yeah. Let me see. Right, so many roads lead to the same percent by weight atmospheres. And the reason, the physical reason for this robustness is that the accretion is largely self-regulated. It doesn't really matter too much what the disk is doing because you can only accrete as much as you can cool. And turns out for percent by weight atmospheres, the cooling times are measured in millions of years, which matches the lifetimes of these gas disks, okay? So you only accrete as much as you can cool while the reservoir, the depleted reservoir, is still around. That's why it is that many roads lead to the same percent by weight atmospheres. That cooling is internally regulated. It's, as anybody who studies convection knows, it's the lid that matters. So the cooling luminosity is set by conditions at the radiative convective boundary. H minus plays a big role. But the conditions there, the opacity there in particular, really doesn't depend, right? You're so deep in the atmosphere that the stuff in the nebula at large doesn't really matter very much. This, I think, this insensitivity, this robustness, the fact that you always wind up with percent by weight atmospheres and that you see them all over the place, this, I think, is a strength of the theory, that you don't need to fine-tune your conditions too much. Sub-Neptunes, where you find one, you're very likely to find a whole bunch. They're gregarious. They exist in these multi-planet families. The orbits of sub-Neptunes today are more or less random. If you plot, if you measure the period ratio between adjacent pairs of planets, you find that they can basically take any value in this continuum of possibilities. Looks more or less random, except for the 10% of pairs which lie near mean motion resonance, the most prominent one being the 3 to 2. So the 3 to 2, the mean motion resonance, where one planet makes 3 orbits for every 2 that the outer one makes. Now, resonance, mean motion resonance, is a signature, I would even go so far as to say smoking gun, of migration, right? So you need to move the planets around a little bit for them to lock into these resonant configurations. So here's just a little animation of this. If you have 2 planets, here and here, and they're not initially in resonance, so the resonance is located is marked by this dashed line. If we allow the planets to migrate inwards, it's a consequence of Lindblad torques. It's a form of dynamical friction with the parent disk, that residual disk. You find that if the orbits converge on one another, that there's the possibility that they can lock into resonance. Notice that the pair is systematically wide of resonance. It's not 3 to 2, it's 3 plus epsilon to 2. And this is a consequence of, again, a form of dynamical friction. Eccentricity damping, which damps the pair to the fixed point, and the fixed point of the resonance is always systematically wide of resonance. It's a consequence of apsidal precession, actually regression in the resonance. I can talk more about it if you'd like, but let me just emphasize that it's always systematically wide as a consequence of this dissipative capture in the disk. Now, I used to think, since only 10% of the systems were in resonance, that I really didn't need to worry about migration for the other 90%. And boy, was I wrong about that. I was corrected on this point by Fei Dai. Maybe some of you know Fei. He's at Hawaii now. Fei has a time machine. And the time machine, those of us working in Origins would kill for a time machine. His time machine is called TESS. TESS is a time machine because it's all sky. So he can find planets that are in young systems. So it's still early days. I think the statistics are plenty good. But 7 systems having ages between 10 and 100 million years. So the young population. And they're in multi-planet families, and you can measure their periods. And you can find that 6 out of 7 of them, he colors the ones that are in resonance, that exhibit resonance, lie within 1% of perfect period ratio commensurability. Okay? So you can make a plot that looks like this: the fraction of pairs that are in mean motion resonance versus time. And if you go back early enough, you find that they're all in resonance at the beginning. So they all migrated to some extent. I think they didn't migrate from very far, not from beyond the ice line at about 2 AU, not from beyond there, because they're not water worlds. At least I see scant evidence for that. But some degree of migration, maybe orbital period changes on the level of 50% or smaller, just enough to nudge these pairs into resonant lock. And after you've locked them, right, from planet-disk interaction, from this residual disk, then your task is to explain how the locks were broken, because that's what the observations demand. So some disassembly is required. Just to get you into the mood of breaking these locks, here's a real system. It's modeled after a real system, TOI 1136, a 6-planet chain, resonant chain. And we've arranged the initial conditions so that some of the resonances, not all of them, are unstable. When they're unstable, the orbits cross. When they cross, like what just happened right there, you get a merger. Okay, you're so deep in the stellar potential well that you don't scatter to infinity. You just cannibalize each other. These mergers are very messy. I don't know if you can tell, but we actually try to account for all the debris that just sprays out from this collision. That debris is subsequently reaccreted. I think another one's going to come up shortly. The task now is to start from a period ratio distribution that looks like this, where everybody's in resonance, right? 3 to 2, 2 to 1, some spattering of second-order resonances as well. And then to go from these initial conditions, demanded by the observations, and then go from here to there, okay? Which is also, this is the observation after 10 gigayears of evolution. And here's where we are right now. This is work by Rixin Li. He's a 51-peg postdoc at Berkeley. And after 10 to the 8 years, this is coming from thousands of clones of TOI 1136. We get them to disrupt, and we create a distribution that looks like this. It's a little faint. I don't know if I was hoping the lights could be dimmed a little bit, but let me emphasize that I think we're getting some things right. We get the fact that the surviving resonances, the surviving resonant pairs, are systematically wide of resonance. You see that from the observations here, okay? And half of that reason we get for free, right? Because we started them there as a consequence of dissipative capture. But the other reason why they're systematically wide of resonance is because all the minor mergers, all that debris flying around and reaccreted by the pair, when you have a resonant pair like this and all the debris is bombarding you from either side, you tend to widen that pair. Okay, so that's the other reason how the widening can be preserved even after all of this instability. Another feature I think that we're getting right is this divot. It's a little hard to see, even for me standing here. But here's the 2-to-1 peak. And just short of it, there's a deficit. See the deficit? There's a little dip in the population just short of the 2-to-1. People have worked on this for many years. But I think I understand where it comes from. It's the fact that the 2-to-1 is special. You don't see the divot in the other resonances, by the way. Okay, not for the 3-to-2 or for the other first order resonances. You only see it for the 2-to-1. And it's because there's a sort of a desert of resonances, low order ones anyway, between the 3-to-2 and the 2-to-1. Okay, there's a sort of a desert there. And so when these towers erode, when the resonant population breaks apart, of course, they create pairs that are distributed over different period ratios, but the destruction of the 3-to-2 creates this pile of pairs here, but that pile doesn't extend to infinity. Because the distance to the 2-to-1 is so far that it can't sort of make it all the way to the 2-to-1 in period ratio space. And so it just sort of, that tail in the population produces a divot in the 2-to-1. And you don't get the same divot for the other resonances because they're just they're crammed too closely together. Yeah. Observationally, yes, it's the most prominent. There are some thoughts about this. First order, of course, is stronger. You can ask why the 3-to-2 and not the 2-to-1. There is a technical difference between the two. The 2-to-1 is affected by the indirect potential, which weakens the depth of the potential, sort of a technical reason. It reduces the capture probability by maybe factors of a few. Okay, so that's one thing one can appeal to. The other thing one can think about, this is more uncertain, is, well, you know, it all depends on where you start, right? So if you start inside the 2-to-1, then you converge, then you'll just hit the 3-to-2 first. Okay, so those are a couple reasons to think about. Okay, so I think we're on the right track, but there are some problems. And this is not this, so we need to fill in these sort of very embarrassing gaps, and hopefully not fill in this gap, right? The divot in the 2-to-1. Maybe the biggest theoretical problem is how do you destabilize the whole thing? What's the trigger for these instabilities? I'll tell you, when you run a standard, people run this countless planet disk simulations to capture these bodies into resonance. You formed all these chains. The torques are so strong, the Lindblad torques are so strong, the co-rotation resonance damping is so strong that you damp these pairs, boom, right to the fixed point. Okay, you can form these long chains, and you start them that way, and you run them for 10 billion years, and let me tell you, nothing happens. They're perfectly stable, right? When they come fresh out of the simulation oven, they're totally stable. And so you need some way to destabilize the system. Not sure what that is. One idea that I'd like to pursue further is photoevaporation, right? The erosion of the planet masses by just a few percent may be enough to destabilize these chains. There was some interesting work by Matsumoto and Ogihara, which is going down this path. So it has the right time scale, right? Because photoevaporation occurs over 10 to the 8 year time scales, which is exactly what the observations demand. That's when stars are most X-ray and UV active. Okay. There is evidence for collisions, planet-scale disruptions happening almost in real time. This evidence comes from debris disks. These debris disks are disks composed of dust created from the smashing together of bigger things. There's a subset of debris disks, so-called extreme debris disks, that are extreme in their infrared excesses. The 24 micron Spitzer excess is maybe 2 orders of magnitude greater than the run-of-the-mill debris disk. Not only are these EDDs, extreme debris disks, very bright, they're also very time variable. So they vary, the fluxes, the Spitzer fluxes vary over timescales of weeks, months, years, suggesting, this is like one of these light curves, suggesting that something happened recently and it's still trying to equilibrate. Our contribution to this, to the evidence for catastrophic collisions, comes from morphology. We've been looking at the shapes of debris disks to see whether we can detect a signature for a collision. And here I'm going to switch gears in the talk to not focus on the sub-AU scales, but to focus on Kuiper belt-like scales where we get the best images. Okay, so I'll be looking at scattered light images like these for these extrasolar debris disks. This is 100 AU scales. For the most part, they look pretty normal, like rings just projected on the sky, sometimes a little eccentric. But this is what's, you see them in scattered light. Increasingly, you see them in the thermal emission from ALMA. This is what the Kuiper belt is supposed to look like at an age of 10 to 100 million years. It has orders of magnitude more mass, maybe 1/10 of an Earth mass, sitting at the top of the collisional cascade, grinding down. They look pretty normal for the most part. But a few of them, maybe a few percent of these disks look really weird. And that's what we've been working on, the weird outliers. So there's sort of 2 classes of weirdness. Winged disks, which have these bright extensions sprouting out from either ANSA, like it's about to take off. 32297 has 2 sets of wings. There's this one, and then there's another one, sort of ghostly, running on top. There are lopsided disks too. It's just like galaxies. Sorry? Yeah, sorry. This is HST, scattered light. Yeah. These are all scattered light. These are actually all scattered light. I think this one is a Gemini image. Some of these disks are lopsided, so short on one side, long on the other. Sometimes the extensions are forked like a tongue. Weird. All non-axisymmetric shapes. So we got to thinking, what's the most non-axisymmetric shape that you can think of? Well, the most non-axisymmetric shape that I can think of is a delta function, offset from the origin, of course. But where am I going to get a delta function? I can get one by appealing to the catastrophic disruption of a body, right? Which will spew out debris. That debris will differentially rotate, smear itself out into a ring. And here's the thing, that ring has a pinch point on it, right? Because all the debris sprays out from that collision point, has some velocity dispersion, but what goes around comes around. So it's going to come back again and all meet at the same place that it started. Not all at the same time, of course, right? Because they all have different periods. But that's where the streamlines will reconverge. And so it's at this pinch point, marking the location of the original collision, where particle densities in the ring will be highest. Particle densities will be highest, relative velocities will be highest, right? Because all the streamlines are converging. And therefore, collision rates, ongoing collision rates, post-impact, right? All this debris grinding itself into smaller and smaller bits, the dust production rate will be dominated, we say here. And we're going to assume that this completely dominates the dust produced from this ring. It is a delta function continuous source of dust, right? Sometimes we call it the singularity. It is the gift that just keeps on giving from the original collision site. And it doesn't move in inertial space, right? Because all the particles just move through it, barring precession, which I can talk about if you'd like. Right. So this delta function source of dust, all the dust that's produced, will be sprayed out, and it'll take this pattern. It's blown out onto these highly elongated, still bound orbits from stellar radiation pressure or stellar wind pressure. It'll be blown out onto these highly eccentric orbits in this pattern. We call these grains the halo grains, and there's a lot of them. There's a lot of them because when you blow out into the halo, you spend so much time lingering at apoapse. There's just nobody out there. Okay, so you're protected from collisions. So your lifetime goes up. As you approach the blowout size, as you get more and more elongated in your semi-major axis and eccentricity, your collisional lifetime goes up, and then in steady state, your population goes up. Okay, because you could just keep building that population out there if there's nobody there to destroy you. Size. Yeah, sorry. This is this DNDS, this Dognani classic size distribution, right? Puts most of the mass at the top end, but most of the surface area, the small, and so forth. But what I'm pointing out here is that because of these elongated orbits, you get a strong it actually formally diverges as you approach the blowout size. Yeah. Oh, yeah, sure. That's down here. That's down here. That's down here. Maybe not so important. Sure, absolutely. They will suffer. You can look at Poynting-Robertson drag. People have looked at that. We looked at that. It's not so important because the particle densities are still so large in the ring that you tend to collide and destroy yourself in the ring proper and not get dragged in by radiation. That's all down here. What I'm talking about is here, all these micron-sized grains that get really thrown out to large distance. There's a lot of them. Back in the day, we used these halo grains to explain the surface brightness profiles. This is surface brightness versus distance, and you can, it's very good fit, actually. Just takes a couple of lines to derive this surface brightness law. In the recently from ALMA is seeing millimeter wave emission from these debris disks on 100 AU scales. And people thought, well, gosh, how could you get all those millimeter-sized particles out there? You don't, right? The usual rule of thumb that, oh, if you're looking at wavelength lambda, that the particle sizes must be lambda modulo 2 pi in size. That rule of thumb fails here because you have this strong divergence. So all of that millimeter wave emission is coming from micron-sized grains. There are just so many of them out there in the halo that they dominate the emission at millimeter wavelengths. That's just all by way of background. What I'm really interested for this talk is this morphology. There's what we call the arc, which is just the parabola, right? It's just the eccentricity 1 parabola marking the marginally bound grains. And then you have these curious jets that come out the backside. I think we understand qualitatively what the jets come from. It's a consequence of two effects. The first effect, two competing effects. The first effect is that the particle densities tend to bunch up near peri, right? Because that's where the collision point is, that's where everybody meets. But the second effect is if you just take a look at a single orbit, the particles tend to bunch up at apo, right? Because they get slower down there, there's a traffic jam. So when you combine both of these effects, the net effect is that you bunch up at neither peri nor apo, you bunch up at an angle that's in between. And that angle that's in between has to be reflection symmetric about the apsidal line. So that's how you get these jets. And I would like to say, for the self-gravity fans in the audience, and I know you're out there, you can try to do this with m=1 self-gravitating disks. You will not succeed. Not to get the jets anyway. Because no matter how strong your eccentricity gradients are in an m=1 self-gravitating disks, you can never get away, we tried, but you can never get away from the fact that the ring will always be narrowest, the radial width will be narrowest over an angle that subtends at least an angle order unity. Okay, so you're going to take this pattern, which is really the Green's function response to a delta function source. You're going to take this pattern, and you're going to smear it out over that cosine, either at peri or apo, and just smear the whole thing out. You do not get the structure. So you really do need a source region that subtends an angle much less than order unity to produce some of these weirder morphologies. We can do it by taking this pattern, this is the face-on pattern, and tilting it over so that the whole wash of grains tilts over so that it looks more edge-on. All the dust is now streaming at you. And the primary wing, that parabola gives you the first arc, and the two jets cohere and superpose to give you this parallel wing on top. Now you can take the whole thing and just swivel it over in azimuth and produce some lopsided disks that way. So this is our go-to explanation for this really weird thing, 32297. I think we're getting most of it right. Some of the finer structures we have a hard time with, but we get, one wing, two wings, one wing, two wings. We even get the bulb, right? All these grains that are just strongly forward scattering their light into your line of sight. How much mass was involved in the destruction? About a Pluto's worth. It can't be too big because the collision velocities out at 100 AU are limited to just a kilometer per second or so, so it can't be too big to take all the debris and just spread it out over large distances. When my colleague Gaspard Duchenne fits the surface brightness profile for this is the same disk, 32297, seen in H-band, he infers a dust grain population roughly about Pluto in mass. Here's another example, 15115. The people call it the blue needle. It's actually two needles. So here's one. It's short on one side and long on the other. That's needle one. But then needle two, you see, I hope you can see it. It's sort of at an angle like this. It's not a diffraction spike. It's like this. Okay, and our go-to explanation is that it's two giant impacts. One that was located here, the other one here. Coming from, actually, in the ALMA passbands, you see two parent body belts. And we can further test this idea, I think, with spectroscopy. I think the grains that you get, I'm not too up on this, but the kinds of grains that you get from high velocity collisions, catastrophic melting collisions, are different from the collisions, from the grains that you get just from gentle sort of erosive collisions. Okay, you might also try to look for silicon monoxide, which is, in these explosive simulations, people find a lot of silicon monoxide gas, which you can try to detect. Here's another example of a lopsided disk. It's lopsided in a very funny way. So this is AU-MIC, everyone's favorite M dwarf. It's a pre-main sequence M dwarf. It's got everything. It's got planets. It's got a disk. And the disk is lopsided in the sense that it has waves. I hope you can see it. This is HST stis image. It's got waves on one side and that aren't really seen on the other side. Now, the VLT resolved these waves with the sphere instrument, adaptive optics. They resolved the waves to look at these undulations, these bright clumps. And over time, these clumps streamed out. They had proper motions that were measured in kilometers per second. Okay, several kilometers per second. The whole thing is just like streaming out like this, only on one side of the star. Okay, so explain that. Well, here's our attempt. We think what happened was there was a catastrophic collision that happened there. Remember, that point doesn't move in inertial space, right? So it's a delta function source of dust. It happens to be located almost along the line of sight to the star. And this collision point is producing all this dust, and this dust, now I'm talking about the unbound grains, it's streaming out, blown out, not by radiation pressure because it's an M dwarf, but because it's an M dwarf, it has a strong wind. So AU-MIC, pre-main sequence M dwarf, strongly flaring in the X-ray. People infer mass loss rates are easily 100 times greater than the mass loss rate from the sun. Now, we say, here's the assumption bit, which is controversial, a little bit ad hoc. We say that this wind is cyclical, just like the solar wind, right? The solar winds or solar cycle, 10-year cycle. So we're going to say that this wind has a 10-year cycle, that it gusts and ebbs, between a low state and a high state every 10 years. Because if we say that, then the dust that's blown out traces this staircase pattern. Every radial zig is when the wind gusts. Every horizontal zag is when the wind is in its low state. And then the disk rotation just carries it from the right to the left. Okay? Of course, you're looking at the thing edge on. And so every one of these radial zigs gives you a very large line of sight column density to give rise to these clumps, which are all streaming to the left. Michael?
Yeah, the numbers that you put into the 2 and 10 to the 3, that amplitude of variation, is that how arbitrary is that? Is that
Oh, yeah, no. So yeah, so this is from, this is based on, good question. There's justification for it. This is based on the X-ray flares. Based on the X-ray flaring activity, you get an estimate of the plasma density. You sort of know how fast it's going, and so you can measure what the betas are. The betas are the force of wind pressure to gravity, and during a flare, you can get up to betas of about 40, which actually correspond to a stellar mass loss rate of 1,000. So it is based on the X-ray data. What's not clear, right, is that all this flaring activity is on hour, I think, or day time scales. What we're saying is that there's a long-term modulation. That's the part that I'm, rather uncertain about. But it works. The velocities are so large that there's actually an avalanche of dust. This I thought was kind of neat. You accelerate these grains to super kilometer per second velocities so fast, they have so much energy that when you collide with another grain, you don't just shatter into 2, you shatter into hundreds of bits. And so you have these showers of grains. It's just like an avalanche. And so there's an opportunity, I think this actually happens, an exponential amplification of the dust flux down one of those radial zigs. And we can get a gain for this dust laser that's about 2 orders of magnitude. And we need this actually to explain how the surface brightness is measured from HST. Without this gain factor in the avalanche, we cannot get the dust cloud masses that have been inferred. It's an object we think that it was about the size of Varuna that just exploded. Varuna is one of the larger KBOs. Yeah. Oh, yeah, so that's yes, this is about what I was going to talk about. So for that particular system, something like, it's very uncertain, but something like 10 to the 5 years. Yeah, it's quite uncertain though. And it brings me to this point, which is, I've made a compilation of, so you sort of have to be lucky, okay? But here's the thing. I've compiled here a list of all the, systems with weird shapes, okay, for morphology. Beta Pic is on here too, the archetype of the debris disk. I can make a case for a giant impact for some of them, not all of them. But the point is, for every exploded Pluto or Varuna, there must be like hundreds of unexploded, Plutos and Varunas running out there at 100 AU. And the calculation is uncertain. It depends on the window of observability, right? How long this signature can be observed for. I can get answers ranging anywhere, depending on the system, between 10 to the 4 years and 10 to the 7 years. And that should be compared to the ages of the system, which are 10 to the 8 years. So what's the reservoir, the source population? I can get answers ranging anywhere from like 10 Plutos to maybe 10,000 Plutos, running around out there at 100 AU scales. And at least in the case of the solar system, I think the Rubin Observatory will, get a decent census, of the larger KBOs out to those distances. So we look forward to that. Oh, yeah. It's a good question. Yeah, no, good. The masses that I recall from our little estimate were about 1/10 of an Earth mass. This is about 1/10 of an Earth mass. Yeah. Okay, we've been talking. I'm going to switch gears again. All these rocks running around in space. Sometimes the rocks fall to the Earth, and we pick them up as meteorites. 80% of the rocks that fall to the ground are chondrites. So called because they're filled with chondrules. These are sub-millimeter sized little BBs that are igneous. They were once molten. Right? You see them here. All these little BBs, about a millimeter to maybe 1/10 of a millimeter in size. When people talk about the age of the solar system, they say, oh, the solar system is 4.5, 6, 7 billion years old. They are referring to the lead ages of these things. So they're the oldest things that we have. I have a sample here, actually, if you'd like to take a look. Just be careful with it, right? You know how to handle antiques. You know how to handle a Ming Dynasty vase, hundreds of years old, right? With care. This thing came out of the oven, literally came out of the oven, some cosmic oven 4.6 billion years ago. So you can take a look. I like looking at the things. Callum and I were talking about this the other day, just recently. I like looking at the things that I'm studying. So they're very beautiful, these chondrites. Okay. They've been a big problem ever since they were discovered by Sorby in the 19th century. Zeroth order problems unsolved. How do you melt them? How do you zap them to 3000 Kelvin? After you zap them, you have to zap them in space so that surface tension can ball them up into spheres. Then you got a real problem. How do you collect them all, right, into a chondrite parent body? You had to collect them with incredible efficiency because these things fill the thing. It's near 100% volume filling fraction. And I like to say, if you can understand the collection problem, maybe you've made some progress towards understanding the problem of planetesimal formation. Big problems. I think the last 15 years, some progress has been made for a tiny subset of chondrites, the so-called CBCHs, carbonaceous type B or type H chondrites. And there, the case can be made, I think it's a good case, that these chondrites, these chondrules were melted from a giant impact. Okay, and we will add to that evidence. Maybe the strongest line of evidence is from the elemental compositions. So to get the right ratios of iridium to iron to nickel, you can't do it with the solar composition gas. Okay, you don't reproduce these elemental abundances. So if you read the fine print, which I cannot because it's all blurred, it will say that you can get these elemental abundances if you condense a gas that is enriched by a factor of 10 to the 7 relative to solar metallicity. Talk about metal rich. Okay, this is what the cosmochemists give us, 10 to the 7. I mean, it's basically a pure metal, okay? So you take this basically pure metal in the astronomical sense, pure metal gas, heated it to 3000 Kelvin. The pressure that they need is something like a fraction of a bar. Now, where are you going to get, right? A pure metal rich gas, fraction of a bar at 3000 Kelvin. You're not going to get it from the disk at large, right? It's mostly hydrogen and so forth. The pressures are orders of magnitude too low. But you can get it from one of these impacts and the hot pressurized gas at that collision point. So what we've done is we've calculated the thermal history of this vapor cloud as it expands outwards. It's a little Sedolph-Taylor calculation, right? You look for this cloud as it expands outwards. It's actually a poor man's Sedolph-Taylor because we don't resolve it in space. We don't bother to, but we do resolve it in time. So we calculate the pressure, the mean pressure, the temperature, the density of the cloud as it expands out, okay? And the reason why we're doing this is because we want to match the observations. We want to see if we can reproduce the cooling rates that are inferred for these chondrules. The cooling rates inferred from the particular mineral structures in the grain. Okay, you can see the mineral structure in polarized light. They constrain the cooling rate, so it's melted, great, but now you got to cool it off, but it can't cool too fast. It can only cool at rates of about 100 to 1000 Kelvin per hour. Whoops, I pressed the wrong button again. Sorry about that. This is really slow compared to vacuum cooling. If you just took one of these BBs and threw it out in space, it would turn into glass, right? You'd instantly freeze dry it. It's orders of magnitude off vacuum cooling. So you need, right, to reproduce this number, you need to bathe it in this like big, thick, optically thick cloud that's slow to cool. You need enough mass in the cloud, right? High thermal inertia, optically thick, to regulate the cooling rates to be about 100 to 1,000 Kelvin per hour. So you need for these clouds to come from asteroids, we estimate to be between 10 and 1,000 kilometers in size, which to me is encouraging because this is actually, right, this is right in the range of the asteroid belt. So that's where most of the mass is. Okay, so the story, I think, holds together to some extent. Now your problem is the Humpty Dumpty problem. And this is, thanks, Roman, for listening to this talk again, but this slide is different. 6 months ago, I said, I don't know how to do this. How do I put everything back together again? Okay, I have an idea now. I have an idea. And the idea is sort of a kind of thermal instability. So you take this vapor cloud, I mean, it's got to have some temperature fluctuations in it. And the regions of the cloud that are a little colder than the rest will have less pressure, just from saturation vapor pressure. It's exponentially sensitive on temperature. So little colder regions will have a little less pressure than the surrounding regions, and they'll be crushed under the overlying pressure of the surroundings. And in compactifying, they will entrain whatever melt droplets are around and bring everything together into these little pockets of hopefully even getting down to solid density. It's similar. I think the instability can be driven by radiation. So, if it's a little colder, it'll condense more. Those condensates, the dust, will radiate more, which will cool more. And so this whole system, the thing, I hope, can run away. So we've computed, just in a very preliminary way, the evolution of these, I call them bubbles, right? These bubbles of cool gas that are compactifying. It's very similar to cavitation that you find, bubbles around submarine propellers. These bubbles are huge. These bubbles are like, upwards of hundreds of kilometers across. And when you compactify, which you can do really fast, right? You could even approach the sound speed in the collapse. When a kilometer-sized bubble collapses, it creates if you can get it down to solid density, you create a parent body that's about 10 meters in size, filled with melt droplets. And there's a size filter too, because you can't entrain things that are too big, right? If the fragments are too big, these collapsing vapor clouds won't entrain it. And when we do the calculation, we get, we can entrain all the sub-centimeter size things. But bigger things are just left outside the bubble. So this is one way to size select for the sizes of the melt droplets that you compactify. Okay, I think I might have several minutes left. Okay, so in the last part of this talk, I will switch gears for just one more time, talk about a final form of death. This is death by vaporization. And it's from the Kepler space mission. It's ironic that Kepler, in its search for life, one of the first things it found instead was a world that was dying. That's KIC 1255. It is a K star, rather old, maybe 10 billion years old, which every 16 hours undergoes a transit, if it feels like it. The transit period is like clockwork. You can measure this period out to like 6 significant figures. What is not like clockwork, which is completely random, is the transit depth. Now you see it, now you don't. Now you see it, now you don't. But most of the time, it's just completely erratic. The depth of the transit is such that the occulting area has to be the size of Jupiter. So a really big thing. But it can't be a hard sphere transit, right? Unless you can think of a way to take Jupiter and make it vanish in 16 hours. So we think what's happening instead is that it's a wind. It's coming off some object, and that wind is full of dust, and it's just really erratic and gusty. That wind takes the form of a comet-like tail. We know this based on the shape of the light curve, which is fast going in and slow going out as it drags the tail across the stellar face. There's a whole class of these objects now. It's not just KIC 1255. Even Beta Pic is everything. Beta Pic, this archetypal debris disk, has a set of what people are calling these shark tooth transit patterns. So what we think is going on is that So what's the thing in the middle, right? What's the thing that's evaporating? It's so close to the host star that the surface is vaporizing. The sound speed of rock vapor is just shy of 1 kilometer per second. So the thing can't be too big, right? Because you need to escape. And so the escape velocity can't be larger than that from an object about the size of the moon. So this is what would happen if you took the moon and put it in a 16-hour orbit around a sun-like star. We think it's sort of close to that, actually, because there's just so much dust coming out of this thing. You measure from the transit depth, about an Earth mass per gigayear coming out from this thing, which constrains it to be close to this upper limit. So what we think is going on is there's this sort of moon-sized, maybe it was a few times that, maybe approaching Mercury in size, just sitting there for 10 billion years and sort of bubbling away. But because the mass loss rate is exponentially sensitive to surface gravity, once it weakens to the point, it can weaken to the point where it just falls off a cliff in mass versus time. Okay, so what we're seeing now, you get lucky, you catch it in this fireworks phase of its demise. To explain the time variability, there must be some kind of limit cycle going on. It's just like the weather, right? So good morning, Kick 1255. It's going to be a real scorcher today. Clear skies, highs in the 2500s. Get ready for that thermal evaporative wind that's going to blow so hard and dredge up so much dust that the 16-hour forecast will be for cloudy skies. And then the surface will cool. The wind will shut off. The skies will clear, right? Whatever dust is in the atmosphere will either keep going to infinity or just precipitate back down, and the whole cycle will start over again. There's a time scale for this cycle. Very conveniently, it is just of order the orbital period, because that's how long it takes for a thermal wind to travel from the surface to the edge of the Hill sphere, where Coriolis forces will turn it out of the line of sight to the star. So there's a natural atmospheric refresh time, right? The dynamical time at the Hill sphere is just the orbital period. So that, I think, nicely explains this on-off behavior. It does not explain what most of the light curve is doing, which is completely chaotic. Here, so here's our attempt to explain the chaos. We were inspired by these very simple 1D maps, right? Chaotic maps. I mean, famously in biophysics, right? The logistic map, it's a quadratic map. Famously chaotic, population booms and busts for like rabbits. So we can construct a map. Our map has 3 ingredients. The first says that the mass loss rate at some time I at the surface is exponentially sensitive to the surface temperature. That's just Clausius-Clapeyron, right? Because that's where the wind base is set by the saturation vapor pressure at the surface. Okay, the temperature at the surface depends upon the overlying optical depth, tau of I, of the overlying wind. And here we just use a Eddington two-stream solution, right? So whether the surface is colder than at altitude or hotter than at altitude depends on the ratio of opacities for these 2 streams. The 2 streams are the radiation coming in, which is starlight and the visible, and then radiation going out, which is the infrared going out. So if gamma, that ratio of opacities, is greater than 3, then the ground is colder than at altitude. We call this the nuclear winter solution. Gamma less than 1, if you're more strongly absorbing in the infrared than you are in the visible, then you have greenhouse warming of the surface. Final ingredient is that you need to build in some memory into the system, some hysteresis. So the optical depth at the mass loss rate at some time I tells you what the optical depth of the overlying wind is at a later time, 16 hours later, that atmospheric refresh time. Okay, this is it. And you just combine. It's not the prettiest looking thing, but it's 1D. It's, you map what the optical depth of the wind is at some time I to a later time I plus 1. And here's what the map is. It's monotonic. This is tau I plus 1 versus tau I. And monotonic, here's the 1-to-1 line. There's a fixed point. And depending on parameters, so here I'm going to use a gamma of 2.5, which is a nuclear winter, sort of a mild nuclear winter. You can, it's a stable point. It's a stable attractor. And you just equilibrate to there. It's sort of boring. That's the steady state, equilibrium, atmosphere, optical depth. But if you increase the gamma, all right, so sort of a stronger nuclear winter, that stable point destabilizes because the slope there is too large. And instead of converging to that fixed point, you actually bounce around it forever, which nicely explains the on-off behavior. You're still not getting the chaos, though. So how do we get the chaos? Well, we get the chaos by thinking harder about the relation, what the gamma really needs to be, well, has to be, depending on what the optical depth is. The kinds of grains that you condense under clear sky conditions, suppose tau is much less than 1, clear skies, gamma cannot be greater than 1, right? Because if gamma is greater than 1, you'll never condense out those grains because you start to condense, oh, you get really hot and then you just vaporize again. So the only way that grains can condense under clear sky conditions is if gamma is less than 1. That means that the grains that condense are relatively transparent in the optical and strongly emitting in the infrared. Okay, so they're sub-black body temperature. And that's things like quartz. Right? You can't condense the iron. It's just too dark, too strongly absorbing in the visible. Just the opposite happens under cloudy conditions. Now temperatures are cool. You're free to condense whatever you want. Iron likes to condense out. You get the usual astronomical silicate, like olivines, for which micron-sized grains, the gamma is greater than 1. So now there's a relationship between gamma and tau. And instead of just getting a pure, nuclear winter or a pure greenhouse, you can actually flip dynamically between these two families of solutions. And so when you fold this in, now the map looks like this. There's still one fixed point, but no matter where you start, it's just completely crazy. And it has a memory, it has a Lyapunov time of about 5 orbits. So that's sort of how long it remembers, like what it was doing. Okay, so I just wanted to show you this as there's more time variability stuff coming out from the observations. And we hope that simple models like these can lend us some insight into what's going on. It's basically where I wanted to stop. The theory is very much incomplete. There are free parameters, depending on what the post-clear sky optical depth is. I can get an equilibrium or a 2-cycle or this sea of chaos. Still, there's still free parameters, I'm sorry to say, in the model. But I think we're getting closer to what's going on. It reminds me of what the poet once asked, will the world end in ice or fire, nuclear winter, or greenhouse disaster? Pick your poison. Well, Kick 1255 picks both. And it changes its mind every 5 days. So, and this is our fate too. If not astrophysically, right, when the sun goes red giant and the oceans boil and so forth, it may also be our fate politically. Given recent events, I think our Lyapunov time is getting shorter and shorter. And on that happy note, I'll stop. So thank you very much.
Thank you very much, Eugene. We've got time for a few questions. I see a hand up from Roland.
Eugene, a question about the destruction of the resonant wall.
Yeah.
So you said that out of simulations, you form things that are extremely stable on giga-year timescales.
From the simulation, yeah.
You showed that your simulations. Oh, those weren't simulations.
Yes. Oh, so you're.
And then the outcomes of simulations.
We made it up. We sampled orbital parameters given the observations. The observations have large error bars. So they were just very convenient set for us to draw from. So they're arbitrary. We just experimented with this arbitrary set of initial conditions, drawn from the observations, and the error bars are large enough that things fall apart. Just to get an idea of what it would look like afterwards. And we were happy actually to get that divot near the 2-to-1. So the puzzle remains. Yeah. Yes, the puzzle remains. Physically, what triggers the instability? Yes. And as I said, I mean, my working hypothesis right now is photoevaporation.
Jeremy?
Going back to early part of your talk, ubiquity of super-Earths and sub-Neptunes explained by formation at a late stage in the disk when the gas is depleted. So even before you got to migration, that raises a question about whether there's enough gas to give you migration and resonances. But putting that aside,
Well, there is. There's plenty of. Yeah.
so has revealed high structures in very young disks, which presumably have plenty of gas. And most people attribute those rings to presence of planets. Those are forming in, but these apparently are not Jupiter mass planets in most cases, because we don't see obvious numbers. So, of course, there are large radii compared to most of it. But what in this picture becomes of those, if they really are planets? Where are they now, and what masses should they have? Should they be Jupiters or?
Yeah, no, the Alma planets. I mean, those are in different scales, right? From the scales I was talking about. Those are 100 AU scales. Yeah.
Anyway,
Yeah.
But, if they became Jupiters, they'd be rather obvious.
The inferred masses, and they're very uncertain, the inferred masses are something like 10, maybe up to 100 Earth masses, but sub-Jupiter. And those masses are inferred, I think, from the widths of the gaps and some assumption about the viscosity.
Because these are very young disks.
Yeah.
So fast out there, and so slowly, it's already.
So Nick Choksey is going to come here. He's a graduate student working with me. He's going to talk about this very problem. Where we've arrived so far is that, well, I don't know what to say. There's a problem. Because if you take these, maybe 30 Earth mass planets in these Alma rings, and you just ask, well, how much gas is there inside the gap? You compute a mass accretion rate. I think it's, the upper limit is given by Bondi. You get accretion rates such that the mass doubling times are shorter than the age of the system. So they're accreting too fast right now, given our ideas about accretion. He will talk about this problem next month. But you ask what will become of them, and I'm saying, well, at the moment, given our calculations, they're accreting too rapidly.
I see one last hand up the back. We'll finish there.
Just a short question, like the moth and the other weird shaped scattered light images, they are quite rare, or are they not really rare? That's one question. And if those systems actually get into denser or high, UV radiation environment, would they actually show similar kind of scattered light images, or do you think that situation would be different for those environments?
On the question of occurrence rate, my very rough estimate is a few percent of debris disks that have been imaged, or a lot of images now, are like that. Okay, so a few percent. Your second question was, what do they look like at other wave bands?
Environment, denser environment than
like
those.
in cluster or something. Well, I think for the moth 61005, I mean, we tried really hard to make a giant impact work for that, but the spurs are sort of coming out at too sharp an angle. So I think actually ISM sculpting remains a good option for the moth. And there you need you need dense ISM that you can get from the birth molecular cloud. It's the usual ram stripping, right? You see it in galaxies all the time. It's just sort of blowing these spurs out. Yeah, that's right. And so I think that works for the moth. For 32297, you can't make it work because it's double wings.
Okay, excellent. With that, I think we'll finish question time, and we're moving on now onwards to Berkeley lunch, per usual. So let's finish up by thanking Eugene once again for a fantastic talk.